Hi there, my name is Robert Harris, and today we'll talk about SemTech, Salt ElectroMining. So, what is SemTech? SemTech is an open source salt electromining technology that uses salt water and electricity to extract precious metals, rare earth elements, and critical minerals. In our continuous mining unit, we use hydrochloric acid, HCl, and sodium chlorate as the leaching solution, both derived from salt water and electricity. The solution has a strong oxidizing redox potential (ORP) of over 1.5 volts at pH of 0. Under these acidic chlorine-rich conditions, it can dissolve noble metals such as rhodium, platinum, and gold, among others. Metals like silver, tin, and selenium are also oxidized and dissolved. I'll make a video about that specific point, and I can't stress that enough for traditional refiners to understand that concept. If you want to use the stannous chloride test to test if gold is in the solution, it won't work. You have to first boil down the solution in order to de-bleach it and allow the gold to be tested with stannous chloride. Because of our closed loop architecture, we can achieve recovery yields of up to 99%, as costs as low as $50 per ton. The system has a small footprint, comparable to or smaller than a vacuum filtration unit of similar capacity. You can feed in toxic heavy metal bearing rock and produce concentrate powder, along with clean silt that is safe for agriculture use. The process generates zero environmental pollution. With Semtech, we turn waste into a profitable commodity. Based on the updated 2025 list of 60 critical minerals, Semtech is capable of extracting all but 4 minerals. 53 of those elements can be extracted and concentrated by the CMU in a single leaching solution. The remaining 3 elements can be extracted by Semtech utilizing the same components, only requiring a slight modification to which leaching solution is being utilized. CMU is not designed directly to extract a barite, fluorspar, metallurgical coal, and graphite because these are primarily recovered as native mineral/compounds resources rather than as extractable dissolved elemental species. However, synthetic pure fluorspar, calcium fluoride, may be created from elements extracted by Semtech. Beyond those 4, the CMU is capable of extracting the remaining critical minerals listed in the following. I'm not going to list them all. There's a lot. You can see them on screen. But point is, they can all be extracted and more and concentrated by the CMU or CEU in one leaching solution. Silicon, titanium, tungsten would require different solvents and solutions, such as hydrofluoric acid or alkaline leaching conditions, in order to be extracted by Semtech, as the CMU requires chlorine-based acids to leach elements. So again, point is, if the elements can be dissolved with very, very strong oxidizing chlorine conditions, it can be extracted. And you have to be really careful with this. Again, selenium, tin, even silver. When I first designed this unit, I did not expect that we'd be able to recover silver. It was only after certain tests, and I'm like, wait a minute, I'm getting silver in my material. So yeah, definitely keep an open mind on what can be dissolved. So even those, listed the titanium and tungsten. I've seen XRF results that show titanium, but that's probably because I use a titanium electrode. So when I scrape off the electrode, maybe that's why. Again, there are certain conditions that might cause titanium to be dissolved and to be plated off. Point is, there's a lot of potential to this technology, and you can see the powders to the right. Those are actual materials that we've processed and plated off. So I wish I had an XRF at the time I produced that, especially that top one. That is a very beautiful. I would use a UV light and it would just absolutely fluoresce, which is a very, very strong indicator of rare earth elements. So let's start off with the CMU, the continuous mining unit. The process operates as follows. Firstly, the acidic leaching solution is regenerated at the anode. This would be chlorine gas, chlorine oxides, sodium hypochlorite, so many different chloride compositions. So I'm not going to go into every single one. But point is, the chlorine oxidizing solution, leaching solution, is regenerated on the positive side on the anode. Then it flows into a leaching tank This could be a slurry system, for example, paired with a continuous vacuum filtration drum. But the point is, we leach the ore, dissolve the metals, and then separate the solids from the liquids. The resulting metal-rich leachate is pumped into the cathode or negative side. Okay, as you see, so we leach out, or we generate the leaching solutions, leach out the ore, however method you want. Right, here's an example of a vacuum filtration drum, and then we pump back that liquid into the negative side. There, the dissolved metals are reduced and plated off as a powder. This powder settles and is collected at the bottom of a cone tank. The now depleted solution then returns to the anode, where it is regenerated again via the cation exchange membrane, completing and repeating the cycle. So, generate the acid or regenerate the acid through the ion exchange membrane onto the positive side. We leach out the ore. The leached solution flows into the negative side, reduces, plates off the dissolved metals, so it would pretty much split apart the gold chloride, lead chloride, whatever compounds are formed into gold, lead powder, or in their oxides, whatever, and then the chlorine onto the positive side. So additionally, keep in mind that multiple leaching configurations are possible. Again, in this case, we'll use a continuous vacuum filtration drum is preferred, vacuum filtration discs, whatever. You could even do a batch leaching, simply leaching through some material, e-waste. But point is, some sort of way that has solid to liquid separation, and these drums include also what I like about the vacuum filtration drum. Not only are they fully automated and continuous, but also, as you see here, what you can end up having is you suck in the liquid. It first dries out this cake layer, right? If we see here in the bottom left, then you can actually wash it. You can wash it, so because there's going to be a little bit of chlorine, a little bit of acidity in the rock, so you can actually wash it, neutralize it, and you're left with clean, solid product. This product could again even be further ran through another stage of a very, very nice washing in order to collect the salts, because if you neutralize the solution, you'll produce salts and so forth. So the key understanding is that we're able to very, very cleanly separate the ore of its heavy metals, wash it very well, and at the end of the day, you have a very clean product. Secondly, the CRU. In addition to the CMU, the CRU, continuous refining unit, operates on the same underlying principle but uses different solutions to selectively separate and refine metals. Specific acids can be chosen to remove base metals from the powder produced by the CMU, or from dory bars or other metal feedstocks, enabling continuous refining. For example, by using nitric and acetic acid, base metals can be dissolved while gold and other precious metals remain, allowing them to be continuously concentrated and recovered. The choice of acid can then be further tailored, repeating cycles to target different metal groups depending on the composition of the feedstock. You can even use more selective acids, such as hydrofluorosilicate, and that one is more selective towards lead. So there's many different ways you can approach this problem, but the whole theory and philosophy of generating the acids on the positive side, running that through the material, dissolving either a select group or a whole group, and then plating them off and regenerating the acid is the fundamental principle behind the CRU and CMU. This is a closed loop process, reduces waste. It has very high recovery yields because you're continuously closed looping the process and so forth. So that's one thing a lot of people don't understand or miss, or about the importance of a closed loop process, because electrolysis cannot plate everything out. You're always going to have a little bit dissolved in the solution. And by having a closed loop process, well, you keep dissolving more new material into the solution that pushes out the old material, if that makes sense. So that's key and critical why we have 99% recovery rates. In fact, you can see lots of studies that talk about electrochemistry, and there's one favorite one that they had three different type of metals, and one had like 100% recovery rate, the other one was 95, the other one was 90, and the reason why one was able to be 100 is because they had other metals dissolved that would allow the electrochemical process to actually push out those ions and allow them to plate off. The solution is always going to need a little bit dissolved, um, you know, but again, by having a closed loop process, you continuously add new ions to be then further plated off. Additionally, one thing I'd also recommend learning is what's called the electron reduction potential, and pretty much this is the required voltage to reduce a material, and typically with higher voltage ions, higher voltage chemical compounds, they actually reduce first before lower voltage ones. So with the CMU or so forth, you can actually run the system and selectively plate off. Typically, what will end up happening is it'll first plate off the platinum group metals, then gold, then lead, whatever, and then the other plate base metals, so on and so forth. But that whole there's so much to electrochemistry. We just scratched the surface. So, the opportunity. Semtech and the CMU can process a wide range of feedstocks, including mining waste, tailings, toxic chemicals, e-waste, industrial byproducts, and many other materials. We have successfully treated diverse ore types as well, including high sulfide and other complex matrix feedstocks. So here's some examples that we've actually ran. The first one is mining liquid waste that we've ran. You can see the clear liquid, and this company ran it through multiple different filtration methods. I they tried many different things, and you can see the material to the right. That is the same liquid. All we did was electrolyze it. It's absolutely beautiful and crazy. Like again, it looks clear, right? It looks like, oh, there's nothing in it. No, it crashed out a lot of stuff, and we proved it with XRF machine that we removed down the lead, and other heavy metals, other toxic heavy metals, and best thing, it costed less than $5 a ton, and it happened in less than 10 minutes. So I mean, I was shocked by that case example. Definitely for sure, one material that I really want to process and run tests on is mining waste. So if there's any companies that got any mining waste liquids, please reach out to me. The second example, and this is actually specifically why we developed the CRU, is refining dory bars. This is a problem that we fundamentally had with our continuous mining unit, right? We produce this mixed metal, but then how do you separate it into its economical value? So the additionally, we also had a company send us out material, this dory bar, and it had vanadium, chrome, manganese, and other components. And what ended up happening is it formed a very hard to dissolve uh, alloy. Right, it's very similar. You could actually compare it to Hastelloy, not directly, not exactly, but the same theory that by having alloyed composition like this, traditional acids, they just struggle to dissolve, but by continuously regenerating the acids and continuously flowing it through, it just eats it through without an issue. So absolutely fantastic. That one was a great example. And then finally, the CMU, just primarily its biggest advantage is the broad elemental recovery. And I'll show that next page, but we have a Rigaku NEXDE XRF spectrometer. Do not use a handheld XRF. They're a scam. I'll make a video about that. But point is, we have a lab grade, very professional spectrometer that verifies our claims, showing a diverse spectrum of rare earth elements and critical minerals extracted. And we also have a third-party analysis showing us actually recovering rhodium. That was actually our first ever third-party analysis we did. Again, I'll talk about that in the next stage. So don't believe our words. Look at the results. Now, I do want to clarify, disregard any iridium readings, as this is a common byproduct error of X-ray spectrum analysis with the presence of lead. Although our ORP, oxidizing redox potential, is capable of dissolving iridium, you know, just if like for example in this sample right here, we have lead at 50% and we see iridium at 0.5%. Do not take that at any value. Whenever you see lead, always be cautious. And I typically notice it's approximately like 1% of the lead value. Again, right here we have almost 60% lead, and we see 0.69% iridium. So whenever you see iridium with lead, it's not a good result. actually got training from Rigaku in order to operate the XRF's equipment, which taught me a lot and educated me why handheld XRFs just do not work. But let's start off right here. We got gold right here, AU. We got PT, platinum. Um, Additionally, we got gallium, CO, cobalt. This is the titanium I was talking about. I don't know if that's just because of the electrode. That one's weird. I mean, honestly, at this point, I kind of feel like it also can extract titanium, but I don't even want to go down that path. So, point is, yeah, you can see a diverse spectrum: zinc, nickel, vanadium, silver, zirconium, cadmium. I mean, just tin. It's just on and on and on. It's this. Whenever you see the commas, that means it's in um, within the margin of error. But here I have palladium. See, it's outside of the margin of error. But point is, again, right here we see various heavy metals. Again, we see a chromium. We also see a bunch of rare earths like deuterium. We see a bunch of different cadmium. A lot of different toxic heavy metals, rubidium, europium, nickel. I mean, I can go on and on and on. Same thing with this. We see the palladium that I mentioned earlier, the germanium, rubidium. Um, yeah, it's. I mean, uh, it does a lot, and the whole point is you have this rock, right, that has sometimes even the parts per million, of critical minerals or whatever, precious metals, rare earth elements, and is able to economically extract that into a powder concentrate. Yes, it is a mix, but then that powder is a mix. It's a economical mix. In fact, there are refiners today that can extract, process this. Though they're really big refiners that are very specialized, whatever. Eventually, we do want to develop a system that, like, you put in material, whatever, and it'll actually separate each individual element. We have a theory and methodology idea on how to achieve that, but right now we're just doing one step at a time. So again, with this sample, we could run this easily through the continuous refining unit. Most of this would be separated and we'd pretty much be left with gold and platinum, for example, if your target is that, so on and so forth. So here's a third party analysis. Sorry that is angled, but right here we see rhodium at 0.11%. And yeah, this was a very happy analysis that I had. This was the first ever time we got confirmation. We have other reports that also show palladium, and right here you see palladium, but higher gold. But the point is the technology works. The theory works, the science works, the membranes work, everything works. It's more about whether or not you're open to believing what's in front of your eyes. So, beyond the mining process itself, the key breakthrough enabling this technology is our ion exchange membranes. We developed an in house formulation using water softener resin and PVC cement. While traditional ion exchange membranes can cost up to $400 per square foot, ours, they only cost less than $1 per square yard. We also have field tested these membranes for months in harsh, acidic mining conditions with no observable decline in performance. Finally, we patented the membrane and released it as an open source under the Creative Commons Zero CC0 1.0 universal license, dedicating it fully to the public domain, as we believe this enabling technology can impact countless industries from agriculture to energy to fuel cells, waste treatment, beyond. I'll explain more of that towards the end. Like, this technology is going to change the world, and yeah. So our mission, well, open source is a core motivation behind our work. Robert Harris, me, my early career, much of my inspiration came from RepRap, the 3D printing community in its earliest days. The idea of self-sustainability through a printer that could print another printer left a lasting impression on me. One of my favorite quotes from the RepRap creator, Adrian Bauer, is, "When my child's feet grow, I just take her old shoes, run them through a shredder with a little bit of extra plastic, like a bottle or something, and print out a new pair of shoes 1.1 times as big, and the child has a new pair of shoes that fit again." That idea has stuck with me. 10 years later, when I was a 14-year-old or 13-year-old kid, I think, hearing that, I'm like, wow, this is huge. And again, this, I really appreciate Adrian Bauer, if you're watching this, thank you so much. Um, because of him, I got into 3D modeling, which got me into CAD work, which allowed me to get a job in construction and primarily field engineering, drafting blueprints, so forth. So yeah, it opened up an entire my entire career. I genuinely probably wouldn't be here and have what I have if it wasn't for uh, him and open sourcing the membrane. Open sourcing his RepRap 3D printers, and now that led to me open sourcing, my the mining technology and the membrane. So I really appreciate it. Thank you very much. But the most important thing to understand is that 2 decades later, RepRap helped shape what became a major force in the 3D printing world, a technology now used by countless companies and individuals. Yet their open source approach didn't hold them back. In fact, while many companies rose and fell over those years, RepRap impacted, endured, and showing that open sourcing is a key enabling technology that can create an entire industry, but where both the founders and the broader world benefit. And a similar opportunity exists here. The battery industry alone is projected to reach approximately $500 billion, something that Semtech drastically helps in unlocking advanced areas like redox flow batteries, an important technology historically constrained by the high cost of ion exchange membranes. But by open sourcing this technology, we enable key drastic membrane technology advantages that rely off existing tech research, but can simply move more easily from the lab to real world commercial production, delivering broad benefits on a global scale. So I can't emphasize this enough. My whole philosophy is that this is going to unlock entire new industries and not entire new potentials. And if I can simply have a fraction of that percentage, if I can have a small portion, I'm happy. I have a farm, I have solar panels, I have a homestead. I don't have any loans or debts at a very young age. But point is, like I got into this because I wanted a redox flow battery. Nobody makes redox flow batteries, so I'm like, all right, I'm gonna make my own membrane because I can't even buy these membranes. They're so not only damn expensive, but back then like you couldn't. It's hard to get them. So yeah, and my favorite quote from myself is, "Everyone wants to change the world, but no one wants to try. Let's try." So here's the problem to understand. All life and industry ultimately depends on chemistry. Even processes like producing concrete or steel are fundamentally chemical, not simply a matter of heat it up and pour out the metal, as many people assume. So take this diagram to the left. Steel making, for example, it begins as a reduction process where coal or carbon reacts with the iron oxide rust to reduce it into pig iron and CO2. Oxygen is then reintroduced to refine that pig iron by removing impurities and excess carbon, producing slag as a waste byproduct and yielding steel with a lower carbon content. As any chemist will tell you, in traditional chemistry, half of the work comes from after the reaction, cleaning and purifying the product you just made. Again, look at this diagram right here. You have iron ore. You mix it with coke and limestone to shape into balls, to then add extra coke to, and then you have to convert the coal into coke in order to reduce the oxides and then melt the ore itself. And then you run that through a blast furnace, and then convert that pig iron into regular steel by injecting pressurized oxygen. It's not as simple as just heat it up and melt it out. No, and there's a lot of energy cost to each one of these steps. And in fact, I made a video recently about that, and how showing how this traditional steel mining process produces steel at around $550 a ton. Semtech can produce steel for less than $200 a ton. Again, watch that video. Very great video. The science is there. The research is real. It's not theory. It's not speculation. The limitation has always been the membranes that we unlocked. So this is going to shake up a lot of industries. So what is the solution? Well, electrochemistry, because it fundamentally works directly at the problem, because all of chemistry is determined by electron interactions. Electrolysis acts directly on chemical molecules to drive reactions, but without control, it can be self-defeating. For example, when you electrolyze salt water, sodium hydroxide forms at the negative electrode, a base, alkaline, and then a chlorine forms at the positive electrode, an acid, Without a separator, those products mix, react together, and effectively undoing the chemistry you just created. But an ion exchange membrane solves this by keeping the two sides separated while allowing specific ions to pass through. That level of selectivity lets you manage reactions with far greater precision, down to the movements of ions and electrons. So there's much less opportunity for loss. In that sense, ion exchange membranes are often described as a form of nanotechnology because they enable control at extremely small scales. Another way to think about this is that an ion exchange membrane helps you control entropy. When you apply a voltage charging, you create an imbalance between the two sides of the membrane. When you draw power through a load discharging, that imbalance moves back to equilibrium and releases usable energy. This is the basic operating principle of a redox flow battery, an energy storage approach that can reach costs of around $5 per kilowatt hour compared to lithium based systems that are over $100 per kilowatt hour. Ion exchange membranes aren't magic, and they do have constraints. For example, they require compatible conductive solutions to operate effectively. But with thoughtful design, many of these limitations can be addressed. Ultimately, what has held back this wave of electrochemical technologies is the cost of the membranes, an issue we've tackled in open source. So again, one example is lithium recovery. So we have some ideas. We're not going to say them yet because we're going to develop them. Properly publish them. Similar how we did the patent, publish it. That way nobody can patent troll afterwards, and then release the technology to the public, open source it yet again. The benefit of doing it that way is that you have a official filing date with the United States government of the technology of what you've created, instead of having to argue in court in the next 5 years of whether or not this is something that's open source. As we know from certain very recent examples with a certain gaming company from Japan, definitely the patent system is not perfect, and companies abuse it all the time. So yeah. So, but again, the most important thing to understand in this aspect is, again, as you see in the diagram, the whole thing that makes chemistry, and chemicals, and bonds, and molecules, and so on and so forth, and compounds. Everything is simply based off electrons moving from one to the other, creating a bond or releasing electrons or so forth. That idea, the understanding that principle, is what allows you to understand, oh, by controlling it directly, which electrons is electricity. By controlling electricity directly with electricity, you have no room for losses, right? Fundamentally, any system, if you don't do it directly, you will have losses. That's just the basic laws of thermodynamics. I like to say that our only competition is the laws of physics. So. Now, why rollout LLC? Well, our primary competitive advantage isn't a single piece of technology, it's perspective. As many people have noted in the comment sections with the other videos I posted, what we've developed is simple and intuitive. It's so straightforward that many people respond with, how did nobody think up of this before? But the logic is clear and the results speak for themselves. All it takes is the willingness to approach familiar problems from a different angle. Take the continuous mining unit, for example. It uses the ion exchange membranes in a novel way to recover dissolved metals from solution. But it does that through a closed loop process. Because again, traditionally, these membranes are used in open loop systems. Acid is purchased or leach out the ore, metals are dissolved, and the remaining solution is discharged as waste. So literally, they'll dissolve rocks. You'll have metal, soluble liquid. You'll run that through the ion exchange cell, let's say just on the positive side, and most of the ions pass through. But remember, like I said earlier, if you don't have a closed loop process, you're always going to have a little bit of ions left dissolved, and that causes problems. Typically, with these guys, mainstream companies, what they'll typically do is use what's called ion exchange resins, which are almost like a sponge for selective metals, and they'll actually absorb the remaining amounts in order to recover them. But these resins are super expensive. They're not cheap. So a lot of headache, and then how do you extract the metal from that resin? It's so many headaches. Some companies, they literally just burn the resin in order to melt out the gold. It's just such a wasteful process. But by closing the loop, we reroute the cathode stream back to the anode And again, this might seem counterintuitive to most traditional chemists because the opposing solutions would normally neutralize each other. But again, by the ion exchange membrane, it bases the ion transport in a way that favors one direction. I like to almost describe this like a diode for chemistry, preserving a potential difference and allowing the cycle to continue. It's an unconventional approach, but it becomes obvious once you step outside of traditional assumptions. The same mindset applies to our membrane formulation. Instead of relying on the conventional and complex process of post functionalizing membranes, we start with pre functionalized resin, widely available and is far easier to work with. Then we use it to produce ready to use membranes. The result is a simpler, more accessible manufacturing pathway without sacrificing performance. Layman terms for what I just said there in the end, most membranes, how they work is they have some polymer, compound, whatever, right? This sheet that they create first, and then they use chemicals to functionalize or activate it. Okay, our key thing is we use pre-functionalized resin. Again, ion exchange ion exchange resins used in water softeners. Um, this is a problem I keep seeing. Even in the video you check in the comment section when I first released the first video and people were trying to theorize how it came up with the membranes. They kept trying to think up of, oh well, he must use post sulfonization of this. Everyone kept approaching it from the wrong angle. Not a single person approached it like, hey, what if we pre-functionalize the ingredients first and then just turn them into a sheet? Nobody, not a single person. It's again, it shows that all it takes is looking at things from a different perspective. So what is the cost and consumables? Semtech involves various operation costs and consumables, but the core system is designed around hot swappable components, such as electrodes, membrane, pumps, valves, and electronics. So repairs are quick, downtime is minimized, and maintenance is straightforward. I can't emphasize this enough. Everything I design with this, I design with intent that it's repairable. It can be fixed, or even you can use the same exact electrolysis use system, swap out a couple components, and use it for a completely different application. I do not want these membranes or this electrolysis cell to be something that you build once. You integrate the membranes, and then let's say the membranes get damaged or whatever because accidents happen. Whatever. And you have to throw the whole thing away. No, no, no. As you see in the right, I have it that you can actually swap out the membranes. I have the electrodes as where there's plug and disconnect, so super super replaceable. Even the valves I have on union fittings because currently I'm using hardware store PVC fittings, and they're not exactly designed for these acidic leaching conditions. Typically, the seals in them harden up and get damaged. Uh, so what I figured is it's cheaper just to have union fittings than to buy a $400 specialty chemical resistance fitting, and then just swap that out every couple months. And you know, I mean, again, it's all about simply thinking of these things from a different perspective. So let's start off with electrodes. Right now, we use coated graphite electrodes, and they typically last 2 or 3 months, depending on usage and the leaching solution. At present, a 50 amp electrode costs about $100 in material, with in materials and time at lab scale. One key area we plan to invest in is improving electrode longevity and cost by mass producing our own in-house glassy carbon and mixed metal oxide electrodes, which can last for years. This is something that I really want to get into. Glassy carbon is something I really love, and a lot of chemists want, but it's just been something that people, companies don't really mass produce because there's not much of a need. And we believe that with this membrane, we've unlocked that need desperately. And again, even the graphite electrodes, they're as you see, there are a bunch of stacks, and it's a bunch of soldering and work and trying to get it all together. It requires a little fabrication plants. It's a lot of time, it's a lot of headache. Can it be automated by a machine? 100%. But I don't have the money to afford the machine, so that's why right now they're about $100. Membranes, we haven't experimented or experienced a membrane failure after even months of use, nearly a year of continuous use. Regardless, the membranes themselves are extremely inexpensive. An entire assembled membrane, as you see, the frame structure costs like maybe $20 or $50. and it's mostly just CNC, CNC machining and fabrication time. Putting it all together, put it in the substrate, spray it and so forth. I mean, it's honestly something that most definitely can really be easily and cheaply mass produced. I'd probably say that whole thing can be mass produced for, I don't know, $5. Yeah. Electrical components. So we use power supplies, obviously, monitoring centers, sensors, pump speed controls like the variable frequency drive, and related hardware, but they're all inexpensive and straightforward. We use off-the-shelf components, literally stuff we buy off Amazon. But it's selectively designed for reliability and to be easily replaced, even in worst-case scenarios. So everything we have, if it breaks down, it's not going to take down the whole system, permanently. Like within literally less than 30 seconds, we have the goal that within 30 seconds you could replace any part. Mechanical components, we use a magnetically driven acid resistant pump to circulate the leaching solution along with a vibratory / ultrasonic mechanism to dislodge plated powder from the cathode. We also integrate a continuous vacuum filtration drum, an industrially proven technology for reliable solid to liquid separation. So like I said, with the mechanical components, I already explained with the valves. We use the pump. Never had an issue with that so far. We abuse the hell out of it. I've run straight, very very sandy and grindy slurry through it. I don't know how it's not eaten up and destroyed, but it works. Again, you're not I'm not supposed to be doing that in the first place, but point is, yeah, these mechanisms, they just work very great. And like I said, I put unions everywhere, so even if I need the pump to be replaced, I can swap it out. But typically with the pump, I more did that in the very early stages because these pumps are kind of expensive. They're like 60 or 80 bucks from China, and it was a lot cheaper for me just to have union fittings. And when I needed one in one cell or one in another cell, I would just, you know disconnect the valve, remove, twist them off, and then reuse them for a different cell because I couldn't afford multiple pumps. But what is the overall cost? Each feedstock has its own processing requirements. For example, leaching largely inert quartz is far less costly than treating high sulfide ore, which can require aggressive chemical burning oxidation to break down sulfur. Under an electric rate of 15 cents a kilowatt hour, operating costs typically fall in the $50 to $200 per ton range. Industrial power is often at 8 cents a kilowatt hour or lower. Having an engineering mindset, I prefer to build in an generous with a generous margin of error. At residential electricity rates, a worst case scenario, I estimate that SemTech operates at around $50 to $400 per ton with the component replacements. So, I typically tell people this, and they don't understand. They're like, "How can you have a large margin of error?" Again, it all depends. If you just are leaching out trace minerals, right? You don't have as much reducing potential to do, because remember, the primary energy consumption is in reducing the dissolved salts. So when you have gold chloride or iron chloride, whatever, the most energy is required in separating those two bonds. But let's say you have a lot of sulfur that you have to deal with. Well, now it's a bit of a different situation because now you actually have to chemically burn and oxidize the sulfur. So actually, remember, we have oxidizing chlorine leaching conditions. So it actually chemically burns it. But even like the iron, iron process, where you have a material that's 90% rust or whatever, right? With that one, you're trying to react with and dissolve a lot more metals, nickel ore, so on and so forth. Where copper ore, where you're not operating at trace amounts, you're more operating in the double digits, or definitely the cost goes a little higher. And like I said, typically well below $200 a ton. But if we double the, whatever, right? Again, I'm an engineer. All right, I know chemists watching this are not gonna like that, but that's just how we engineers, with our engineering mindset, think. So, yeah, still insanely economical. So, what are our futures, plans, and objectives? Well, firstly, scale up. We've already run Semtech at the 10 to 50 pound scale and produced materials with verified results. The next step is to scale to a system capable of processing tons per day. an essential threshold for economical viability in mining, since ore and e-waste are relatively low value feedstocks. Typically, a 1 ton will have around 1,000, maybe $500, $5,000 per ton. A lot of people message me or leave comments like, "Oh, if I have this unit, I'm gonna make it rich by processing a couple motherboards." No, you're not. I'll make a separate video about this, but yeah, a lot of people just don't understand fundamentally, basic truth. And one basic truth they don't understand is, okay, if you're going to enter into something, understand fundamentally what is that material worth, right? How much of gold is there? Because you can't, this is an alchemy. We're not extracting, we're not creating gold. We're simply extracting what's already there. If there's only $1,000 worth of gold in a material, in a whole ton, you're going to have to process, at least, a ton or two a week, in order to like make it worthwhile. Honestly, I mean, $2,000 a week is a pretty, there's a lot of salary, a lot of jobs that plumbers make that much. So again, that's why you really have to be processing tons per day in order to make it worthwhile whatsoever. Plus the heavy equipment, plus this. I mean, just scaling up, it's a whole thing of its own. But and again, so this is something we're trying to do next. But reaching the ton per day scale will require initial research and development, and the development of basic manufacturing capacity. Because again, like the electrodes, they're a bit, not complicated, but just labor intensive. And it's something that you need to hire people. You need proper space. You need proper equipment to produce these at a bit of scale, because I'm gonna have to produce probably close to, I don't know how much the 1 ton unit is probably gonna be. I mean, it'll probably just be a couple dozen. But again, that's one unit. Sure, you could one pilot scale unit. Sure, you can go through that. But when you're trying to make multiple, trying to test multiple systems, you need a small manufacturing facility. And fundamentally, at the end of the day, we're going to need mass production. So the next step overall is scaling into mass production, so that we can manufacture these electrolysis cells and their supporting components cost effectively at volume. We also need the right lab space and analytical equipment to run accurate mass balance testing on ore samples down to the parts per billion level. So far, we've only scratched the surface of what this technology can do. Right now, I'm using a Rigaku NEXDE. That one is a little over $60,000 with all of its components, almost $67,000. And it's a great machine. Absolutely love it. But it's limited, right? It can't get down to accurately in the lower parts per million range. Depends on the matrix, depends on the composition. Some stuff it can, some stuff it can't. But for us, we're dealing with too many incidences where we need to get to the parts per billion range, especially if we want to do a quantified analysis of, okay, how much material is in this ore, how much did we extract, how much is in a material and or after we extract it, and so forth. Right now we can't analyze it. Literally, our best way of analyzing is running the material through the system, leaching it out, and then analyzing the end composition. Now, to clarify some points, how I came up with a 99% recovery rate. What we've ended up doing a long time ago was we added controlled amounts of a material, electrolyzed it out in a very, very small, controlled batch. Electrolyze it, or ran it through the system. That's how we obtained our 99% recovery rates. In that case, we added, it was point no, it was zero point 0.5 grams of gold that we added, and we're able to recover most of it. So again, there's so much to this technology we would like to do, but you need analytical equipment, and they cost like $300,000-$400,000 each. But at the end of the day, if you're a regular person, and how can you help? This is actually the most important thing. Please help us share this technology, spread the word around, connect us with media, collaboration opportunities, podcasts, so forth. Our main goal is to scale the system and secure proper funding for continued development. Scaling isn't a DIY challenge, it's an economical one, and it needs real resources. So, existing work. ROA LLC has already built a dedicated laboratory for this open source technology. Beyond the roofing, framing, and concrete you see in the first picture, with those guys up there, I constructed everything else. Literally everything you see in that picture. I did it myself. I mean, I had some help with my dad or even my wife to put up the vinyl sheeting you see, the tile looking stuff, but every single thing, the second floor, I basically did that myself. The insulation, I 100% did that myself. The sheet metal, I mostly did that myself. The interior walls, I did that almost entirely myself. The electrical myself. Air conditioner. I mean, every single thing you see in there is pretty much myself. And I'm yeah. Um, and this took me about 3 months to do. Honestly, closer. Yeah, about 3 months. Um, and I hope, I don't know, every single time I look at this, I feel really proud. It was a lot of work to go into this, and I remember when I finished, I was always depressed. I'm like, oh, it's keep thinking I'm gonna finish next week, next week, next week, and I'm like, oh man, it's taking so long. And I look back at my pictures, and I'm like, oh, that was only a month ago, and I'm like, oh wow, I'm actually doing a pretty good job. I'm a person that always pushes myself, and I always feel, I wouldn't say depressed, but I feel down until I actually get to the end results. And um, yeah, as you see, I'm happy in that last picture. I finally got it done. Mostly, I mean, again, it's all about money, but I mostly got it done to the point that I have money left. So here's a DOE grant that we're applying for, an example of cost. So a lot of people, they just don't understand, like why it would cost a lot of money to do this. And honestly, this is not a lot of money. You can constantly see in the news reports, to companies spending literally, billions of dollars, tens, $20 billion. I mean, $100 million, is nothing. I remember I talked with another company, and they were bragging, and they're trying to like create this collaboration mining thing with a couple of different companies. They were bragging, oh, we're working with this other mining technology, and they were able to raise, I think, 60 or 80 million dollars, and blah blah blah. And I'm like, okay, and what did they achieve with that, right? Like, again, I achieved all, that whole facility for, I mean, I don't know, I want to say less than 50,000. Like, I achieved this technology for pennies on the dollar. We can do a lot with very little money, and $10 million is very little money in the grand scheme of these, in order to mass produce a mining technology that is immensely cheap. So, again, to the right, you see examples of the cost requiring scaled technology properly and responsibly, both to build a fully developed pilot-scale system and to establish mass manufacturing capability. Some items such as wavelength dispersive XRF and ICP-MS are high-end laboratory instruments that require specialized lab space and costly installation, and the equipment itself represents a major cost. I can't stress this enough. This is something that we personally messed up with. There's a company that was helping us out with funding, especially for XRF. And the biggest thing that we made a mistake with was buying a Chinese XRF. In fact, I have an older video you can find that about, and it ended up being a complete scam. Couldn't do what it did, and we ended up spending almost $18,000 on that machine after tariffs and shipping. So $18,000, we're able to resell it to a jeweler store, because it does okay. It does good with like solid gold rings, but you know we purchased it because we needed broad spectral analysis on powders and liquids, and it can't do that. So anyways, we're at least able to recover, I think, $8,000 on that, but still $10,000 lost. Months of headache, frustration, stress. The Rigaku one, I'm so happy with. That one was the best purchase. It was a expensive purchase, but honestly, they have a pretty fair price. And at the end of the day, again, so you can see the ICP-MS machine, we already have quotes for this. This is something that costs over $400,000. Wavelength dispersive, same thing. And not only is this just for the equipment, but also facility space. You need a really, really clean room to operate this equipment. This is getting into some really high-end stuff. And this is not something that you just have in a garage or whatever. So it needs its own, little room and its own climate controlled area, so forth. Even some of these equipment like the WDXRF, like they actually recommend to put I think it was copper, but anyways, point is something to protect electromagnetic interference in the room. So like copper lining, so forth. So yeah, and we can see the rest of the budgets again. research team salary, labor employees, chemists, engineers, chemical engineers, injection molding equipment, and when I'm saying $700,000, that's for a used one. Anyone watching is like, what the hell you mean $700,000 for an injection molding machine? There are millions, but yeah, but we're fine with a used one. Certain stuff like that, I have the expertise on rebuilding, fixing, even making my own. So definitely we're fine with that on saving a little bit of money and buying it. But still, even with the injection molding machine, you need a pretty good CNC machine in order to make your own injection molds. And I know people again are going to be like, oh, that costs millions of dollars. Not really. If you're trying to get a really finished high-end product, sure. We're fine with crude quality. So honestly, we're more than fine with going crude on that. We're not trying to make something crazy. um, Basic manufacturing equipment, safety equipment, supplies, materials, chemicals. The facility itself, we're looking, it costed millions of dollars. This DOE grant specifically, we didn't do it as a lease, we did it as a purchase because it specifies that the project has to last for over 10 years. So that's why we ended up just doing a purchase instead of a lease, because at that point it's cost the same. So yeah, again, third-party analysis, facility modifications, insurance, utilities, travel, miscellaneous. It all adds up, and these are very reasonable costs. Most businesses, this is actually incredibly underpriced, and we believe we can do this. We're very confident with $10 million we can get this done. So the opportunity, one of our biggest takeaways from 2025 is that, like I said, some expenses can't simply be avoided or DIY'd. We spent over a year trying to analyze our material using improvised low-cost chemical methods and saw little meaningful progress. We also learned the hard way how difficult it is in the US to find labs with specialized experience required for platinum group metals or this advanced research I'm doing. There just isn't labs that do this. And the reason why is because most production of platinum group metals are done in Russia and South Africa. There's no mining industry in America, therefore there's no refining industry in America, therefore there's no analytical services in America, therefore we've contacted hundreds of companies, we've contacted refineries that work with the US Mint, and the repeating answer is you have to reach out to these international companies in order to do any sort of work. And they're like months lead time if you send out a sample. And yeah, it's just, this isn't something that exists in America. And I like to say that I'm trying to solve. There's three problems that I'm trying to solve. Firstly is the mining technology that is capable of extracting these resources economically. Secondly is the refining technology capable of separating these resources economically. And thirdly is the analytical services capable of providing analysis for researchers like me or mining companies themselves to know what's in their ore. This is a way harder problem than you realize. And like I said already about Chinese XRF, like if you try to cheat, you're gonna get scammed. And analytical equipment is something that's just, there are professional companies that that invest in immense amount of resources to develop their own analytical equipment, their own samples and controls and so forth. And I actually looked into this. I actually wanted to build my own XRF equipment, and I realized simply the calibration material, the calibration elements I needed to buy would have ended up costing, and $5,000 or $10,000, plus the headache, plus the time, plus everything else. So some things need money. But again, with the right funding, our progress accelerated quickly. We moved from a rough prototype, so you can see on the top right, that was our rough prototype, but we even that rough prototype, I achieved it in within 2 or 3 months. And then after that, that's where the year delay happened, trying to find someone to refine and get analyze our material. And then after that, we got proper funding again, got our own analytical equipment. And again, you see the bottom left and bottom right units. That's the latest unit with the interchangeable membranes and so forth. But point is, this latest unit, again, we reached that point in a couple of months, and then we reached the next roadblock. So when we have the right money, we move at an incredibly fast pace. But when we don't have money, again, like the last pretty much half year, pretty much you're stuck. So hopefully the grants will pull through, but otherwise, that's why I'm making these videos. Please, somebody, if you're interested in saving the world, please reach out. um, yeah. So, and I really like this. Really early on, um, I remember, again, you could see this crude cone tank. This is something I bought from some guy who like had a bunch of junk in his backyard, and he had this for $50. I welded up the stand, but point is, I mean, going from this to this beautiful thing with a clear PVC sheet. I mean, just this PVC sheet costs hundreds of dollars plus hundreds of dollars of shipping. This is expensive material that I never in my life could imagine I would ever buy. I remember when actually we started. we 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 had the dream. We had the if only we could buy a used handheld XRF. Oh, if only we could buy a used handheld XRF. That'd make everything that'd make everything we'd ever want. And now I have a Rigaku NEX laboratory grade desktop spectrometer, and well, went went through quick with that one. So yeah, I can't stress enough. Even now, we've only scratched the surface. So here's some potential applications for Semtech ion exchange membrane electrolysis platform. As Semtech core stack manufacturing and mining unit build out matures, the same electrochemical architecture can be adapted to adjacent membrane electrochemical systems with minimal redesign, often by reusing the existing cell hardware. For example, fuel cells, membrane fuel cells that convert hydrogen directly into electricity. Even they work directly on ethanol, methanol, or ammonia. You directly feed into the fuel cell, converting the fuel directly into electricity and emitting clean outputs such as clean carbon dioxide and water. No harmful gases like NOx, carbon monoxide, particulates, etc. None. Some example companies are listed above or below of that. Next thing is e-methanol production. This one I like to describe as producing gasoline from air and water and electricity. Fundamentally produce hydrogen that is combined with captured CO2 to synthesize methanol, a e-fuel, and chemical feedstock. That methanol then you can actually convert into regular gasoline or even diesel or you can make motor oil. So there's actually companies that are doing this where they're building these like that rooftop size, not rooftop size, but a unit you can put on your roof or whatever, and it'll make gasoline from thin air and electricity and water. So again, this is real companies listed, as you see. So this is not theory, this is not speculation. Redox flow batteries, again, as I explained before, you use membranes to separate the potential, entropy potential, and it provides scalable long grid storage. Example companies include the following. Typically, ion exchange membranes, they're half the energy density of lithium, so they definitely are not a direct solution to everything. But grid storage, even heavy equipment, which is what I wanted to use them for, they make huge, huge, huge benefits. So they work absolutely amazing in those cases. Hydroponic nutrient and pH control. So those that don't know, with hydroponics, there's a lot of management that goes on, and with electro membrane ion exchange management, we can control the nutrient balance, pH stabilization, and reuse the water in controlled environmental agriculture and hydroponics. There's a study that shows you can increase the yield of hydroponics by 40%, the yields up to 40%. And again, the fundamental understanding to understand is you regenerate the nutrients you need and eliminate the waste. Same exact principle, but in terms of hydroponics. Even weirder stuff that people don't even didn't even cross their mind or ever heard of is, for example, salinity gradient power, reverse electrodialysis or osmotic power, and pretty much you can create electricity from mixing salt water and fresh water. Again, there's real companies that do this. They even have entire power plants that do this. The cost is simply the membranes, and a lot of times with these cases, for example, they tried one, I think, in Norwegian a while ago, and they went bankrupt because the cost to replace the membranes is more than the power they produce. But again, we solved that with these dirt cheap membranes. And then finally, just general manufacturing, like I said, everything is chemistry. Something as simple as mining, but you can produce you can produce sulfuric acid, you can produce sulfuric acid from gypsum, you can produce I already said chlorine and sodium hydroxide from salt water. You can produce nitric acid with fertilizer. I mean, the application of this is so immense. It converts dirt cheap compounds that has the elemental compounds you need into high energy potential chemical structures at the most efficient way possible, because like I said before, chemistry is electrons. So remember, these are all real technologies with real research papers and real working units. This is not a theory or speculation. This is real. So thank you for watching. This is the end of it. This is my way to reach out, irowow at gmail.com. I'm located in Florida, in America. I also have a website that I need updates, but I highly recommend just staying in touch with my YouTube videos, my YouTube channel. And yeah, I'll keep uploading. I'll keep pushing out stuff. If you're somebody that's willing to help out, please reach out. This means a lot. And yeah, the applications, this technology is really immense. So thank you for watching. Stay subscribed and leave a like. And remember, the most important thing you can do if you want to help is share this content. Let's get this technology viral. Thank you.